And here's the answer to the question or the questions. So first the normal form, it's given below. This is the matrix that you should design with the payoff as element in the boxes and then the strategies alongside the matrix. And then in B, we have to determine the Nash equilibria. We use the check method. And doing that, you will see there is one box with two checks. So that corresponds to the Nash equilibrium of this game, which is unique. And the unique Nash equilibrium is to advertise for both companies. That's the equilibrium of the one-shot game. Then we move to the extensive form of the game, when the game is played sequentially. So GRU moves first needs to decide whether to advertise, and then followed by PTI, who can observe the decision made by GRU. And then again, going through the options, conditional on GRU advertising, it's optimal for PTI to advertise as well. Given that GRU doesn't advertise, it's optimal for PTI to advertise. And then comparing these two branches of the tree using backward induction, it turns out that it's optimal for GRU to advertise as well, because 30 is more than 20. So to summarize, if GRU decides not to advertise, PTI will. So this is not chosen. This is the one that is chosen. If GRU decides to advertise, then PTI will advertise as well. So we have two branches left for GRU to consider. If it doesn't advertise, PTI will advertise. If it advertises, PTI will advertise as well. 30 is more than 20, so it will advertise. And the Nash equilibrium in a sequential game is for both firms to advertise. And of course, this equilibrium is the same as the Nash equilibrium of the one-shot game, where we also observed that the equilibrium was to advertise. So, and this is because both firms in this game have a dominant strategy to advertise. So they don't respond at all to what the other firm does. So even if you observe what the other firm does, it doesn't change your strategy to advertise. And there's no first mover advantage to GRU. It gets 30 just as in the simultaneous move one-shot game. And that completes the question. So we continue with sequential games, and also we continue with commitment. So let's consider another game, play or pass. And we have two contestants here, two players, Dan and Patrick, who play the game. And a coin is flipped to determine who moves first. And suppose now that Dan wins. If Dan chooses play, then the game ends. The game is played with Dan, and he receives a payoff of 1, and Patrick receives minus 10. If he decides to pass, then the game moves to Patrick. If then Patrick chooses to play, Patrick will receive 12, Dan will receive 0. If he chooses to pass, then each player will receive 11. So again, this is a sequential game because Dan moves first and Patrick observes Dan's choice when it's his decision to choose. So we can model it in extensive form using a tree. So Dan first needs to decide whether to pass or play. If he plays, then the game ends. And he receives 1 and Patrick receives minus 10. If he decides to pass, then it will be Patrick's turn to decide whether to pass or play. And if he plays, he will earn 12. If he passes, then both players will earn 11. Given that this is a sequential game, we will solve by backward induction. So what is optimal for Patrick to do? So we first look at the subgame that appears over here. So given that it's Patrick's turn, it's optimal for him to decide to play because 12 is more than 11. And Dan is very much aware that when he decides to pass, then definitely Patrick will play because he assumes that Patrick is a self-interested, rational player. So given that Dan knows that if he passes, Patrick will play and he will end up with a payoff of 0, it's better for him to play himself, which earns him a payoff of 1. So he will choose to play. And the subgame perfect Nash equilibrium of this game is for Dan to play and for Patrick to play as well, although we will never in practice arrive at the point that Patrick gets the option to play, because Dan will always play. This equilibrium is clearly suboptimal for both players because, well, Dan receives 1 and Patrick minus 10, which is clearly much less to both players than both players passing and both receiving a payoff of 11. So how could we change the game structure to allow the players to reach a better, a more efficient outcome that increases the payoff to both? So that would be a Pareto improvement if the payoff to both players increases. One possibility is to use a side payment. So the key is for both players to use strategic moves and an action early in the game that favorably influences the ultimate outcome of the game. So if we return to the play or pass game, what might a side payment, a strategic move that influences the ultimate outcomes of the game, look like? Well, Dan has no incentive to pass because Patrick will always play, which leaves Dan with nothing. So how could Dan bribe Patrick into playing or into passing the game such that they both receive a better outcome? Well, Dan might offer Patrick a deal to pass rather than to play. Suppose that Dan promises to pass and give Patrick a side payment if Patrick will pass too. So Dan tells Patrick, look, I will pass, I promise you, and then if you pass as well, then I will offer you a side payment from my 11 that I will receive if we both pass. That will change the final outcomes of the game. And then the question is, how much does Dan have to promise to Patrick in order for Patrick to get the right incentive to pass? The solution is that a payoff of 2 will do, as that will make Patrick better off passing than playing. So what will that side payment look like in the tree? This is the original game with the original final outcomes and payoffs. So now suppose that Dan promises the side payment of 2. Then instead of earning 11, Dan will only earn 9 because 2 of his payoff is passed to Patrick. So he makes this credible promise of a side payment, which makes Dan ending up with 9 instead of 11 and Patrick with 13 instead of 11. And now you observe that if this promise of a side payment is credible, then Patrick will be better off passing instead of playing because 13 is more than 12. So he will do so, he will pass, and Dan now can be confident that if he passes, Patrick will pass as well, because now it's in Patrick's self-interest to pass. And they will reach the outcome pass, giving Dan an outcome of 9, which is much better than the 1 that he would get from playing the game, and giving Patrick a payoff of 13, which definitely is better than the minus 10 that he would receive if Dan would play the game. So side payments enable players to reach a better outcome. That sounds like a good idea, but in real life, it may be that Dan or people in the position of Dan have an incentive to renege on the promise to make the side payment. So suppose that Patrick decides to pass, and then Dan says, oh, great that you passed, but I won't pay the payment that I promised you. And then, of course, it will not work. So commitments that are not enforceable are referred to as non-credible threats, and an empty threat or an empty promise that is made by one player in a sequential game. So to avoid that dilemma, the players must make a commitment that is credible, that the other player knows will be fulfilled when push comes to shove. So how can a player make a commitment to or a signal to the opponent that the commitment, the threat, or the promise is credible? Let's look at a practical example of entry deterrence as appears in real life. So if you look at competing firms in an oligopoly market, then one of the strategic moves that a firm might want to make is to deter other firms from entering the industry, because more firms means more competition, less market power, lower prices, less profits. So consider the market for tablet computers, and suppose that currently Apple is the only company making tablets, but a competitor, Samsung, is thinking about entering the market. How can Apple make a credible threat that will prevent Samsung from entering its market? So what options does Apple have available? First thing that Apple could do is to threaten a price war, saying, Samsung, be aware, if you enter the industry of tablets, then I will reduce the prices of my tablets to such an extent that you will not be able to make any profits in this market. So you better not enter the market. That is a threat. Question is this a credible threat? Well, let's model it as a sequential game. So the entry game may look as follows. So first, Samsung needs to decide whether to enter or not. If it doesn't enter, it will not earn any profits, and Apple will make some handsome profits of 2. 2 doesn't sound a lot, but the 2 here denotes 2 billion, so that's a nice amount. And if Samsung enters, Apple threatens with a price war. So if it will start a price war, then prices in this market will become pretty low. Samsung will make a loss, definitely not very attractive to Samsung, but Apple will also suffer because its profits decrease to 0.8 billion. If it observes Samsung entering the industry and it doesn't start a price war, that's good news for Samsung, because Samsung then will be able to reach positive profits, but also the profits of Apple are higher than when it would start a price war. So if we now look for the subgame perfect Nash equilibrium here, by applying backward deduction to each subgame, we observe that given Apple finds itself at node B and has to decide, observing that Samsung has entered, whether to start a price war, then it will come to the conclusion that it's not in its self-interest to start a fight war, to a price war. So the price war threat is not a credible threat, because once Samsung has entered, it's optimal for Apple to respond by not starting a price war. And Samsung knows this. Samsung, if it reads the game correctly, knows that the threat of a price war is a non-credible, it's an empty threat by Apple. So it can safely enter. It knows that that Apple will not fight, and Samsung will get profits of 0.5, which is higher than the profits if it doesn't enter the industry. So the subgame perfect Nash equilibrium here is for Apple to not fight and for Samsung to enter the industry. So the threat of a price war is not a credible threat and will not be sufficient to deter Samsung from entering the industry. What else can Apple do? Well, Apple could also invest in excess capacity in anticipation of entry, which puts itself in a better position for a price war, because then it can also increase its output and flood the market with tablets. So now suppose that Apple does that. It has invested in expanding the capacity, which changes the final payoff that Apple receives in case of a price war. If Samsung doesn't enter, Apple's profits are now lower than 2 billion because it has invested in this excess capacity, which it doesn't need because Samsung doesn't enter. So the profits go down to 1.2. But if Samsung enters and Apple starts to fight, and it can use this excess capacity to produce extra tablets, then Apple's profits will be 0.8. And if it doesn't fight, then it will not sell the additional excess capacity. It will not use it to produce extra tablets, and its profits will be 0.6. So given the excess capacity, it will be optimal for Apple to start a price war once Samsung has entered. And Samsung, observing that Apple has this excess capacity, it knows that the threat of a price war now has become a credible threat. So investing in excess capacity has the consequence that the threat of a price war becomes a credible threat. And Samsung knows it, and this will prevent Samsung from entering the industry, because minus 0.5 is less than zero profits that it has from not entering the industry. So as an incumbent firm, like Apple is in this situation, it's worthwhile to invest in excess capacity. In the end, it will never use the excess capacity because the competitor will not enter. And if it doesn't enter, Apple will continue to be the monopolist. But still, it has value because the excess capacity has made it possible for Apple to deter entry. So that brings us to the end of this lecture, where we discussed quite a number of topics in game theory. We started quite easy by describing what is a game. Then we looked at the different strategies, whether firms have a dominant strategy, dominated strategies, and we tried to solve for the equilibrium outcome. And to that end, we also introduced the concept of the Nash equilibrium, and we distinguish between one-shot games, repeated games, finitely or infinitely repeated games, and we looked at sequential games and the value of moving first or being able to make a credible threat. I think that in this course we really studied a lot of the core topics in microeconomics, so you really learned a lot, but of course there's a lot more that we cannot cover in this course, and I necessarily need to refer you to the follow-up courses that are taught at the Faculty of Economics and Business. And to assist you a little bit, in case you're interested in doing more microeconomics, I've listed the follow-up courses there. There's the second year bachelor course, Industrial Organization, that really goes into the strategic interaction that happens between firms if they are in an oligopoly market. So what happens if firms have market power, and what can regulators do in order to reduce the market power that is enjoyed by firms? And how do firms collude, and how can you prevent collusion between firms? And the third year we have intermediate microeconomics, which is a rather technical course, which covers similar topics as the course that we just finished. But in addition, it also covers the topic of asymmetric information. So what happens if not all parties active in the market have the same information? And also in terms of game theory, there we will also look at mixed strategies. So what if firms do not play the strategy with probability 1, but they can mix between different actions? And how do firms and individuals deal with situations of risk and uncertainty? That's not a topic covered in intermediate microeconomics. Then there's a minor course in environmental and resource economics. So that will emphasize externalities, especially the negative externalities of pollution, and how to design policies to fight pollution. And there's another minor course in behavioral and experimental economics, where we also lift some of the assumptions that we maintained throughout this course. What happens if players do not always act rationally, but sometimes also use rules of thumb or heuristics to determine their choices? And there's even more. If you move on to the master, there's a course in games and industrial organization, more on firms with market power. There's a course on competition policy, how governments should deal with market power, the economics of regulating markets. So for example, for energy markets, there is not a natural market for energy because energy companies enjoy a natural monopoly. How should governments regulate those markets? Then we look into the household in microeconomics of household behavior. So if you have a husband and a spouse, how will they allocate their time between work and leisure? Also in the presence of children and also over time. So a household will be looking forward, not only optimizing today's decision, but if you anticipate that you will have children, how will that impact your labor market choice decisions today? And then finally, there's public economics and social policy. So how should governments design policies to bring about equality in society, fair outcomes in society? How should public goods like the national defense be provided? And how should government deal with externalities of consumption and production decisions? So that in a nutshell are the follow-up courses, but first you need to complete this one. I say goodbye and wish you all the good luck with this course, finishing this course and in your future studies.